This video covers Part 3 of Section 3.7, Division into Cases. In an earlier example, we saw how introducing the two cases, n is even or n is odd, was useful in proving a result about integers. We now want to introduce an important theorem in number theory that generalizes this idea. The theorem is called the division algorithm, and this is actually a result that you're familiar with already from elementary school. It may not have been stated in quite the same way that we're going to state it here, but after you see what it says, it should look somewhat familiar. So the theorem tells us for all integers n and d with d greater than 0, there exist unique integers q and r such that n is equal to dq plus r and 0 is less than or equal to r is less than d. The proof of the division algorithm relies upon mathematical induction, which we'll consider in a later section. For now, we're interested in learning how to apply the theorem. We'll begin with a few simple examples to gain some familiarity with what the theorem implies. In general, the theorem says that when an integer n is divided by a divisor d, then there exists a quotient q and a remainder r satisfying the two conditions. N is equal to dq plus r and 0 is less than or equal to r is less than d. To see what this says, let's look at the following example. For each of the following pairs of integers, what can we conclude from the division algorithm? For our first pair of numbers, we'll take n is equal to 31 and d is equal to 7. So d is the divisor, so we're going to be dividing 7 into 31. According to the theorem, there exist unique integers q and r such that 31 is equal to 7q plus r and 0 is less than or equal to r is less than 7. The unique integers q and r satisfying these two conditions are q is equal to 4 and r is equal to 3. We have 31 is equal to 7 times 4 plus 3, and 0 is less than or equal to 3 is less than 7. When 31 is divided by 7, we obtain a quotient of 4 and a remainder of 3. For our second pair of numbers, let's take n is equal to negative 31 and d is equal to 7. According to the theorem again, there exist unique integers q and r such that negative 31 is equal to 7q plus r and 0 is less than or equal to r is less than 7. The two unique integers q and r satisfying these two conditions are q is equal to negative 5 and r is equal to 4. We have negative 31 is equal to 7 times negative 5 plus 4, and 0 is less than or equal to 4 is less than 7. So what this means is that when negative 31 is divided by 7, we obtain a quotient of negative 5 and a remainder of 4. Now note that q is equal to negative 4 and r is equal to negative 3 will also satisfy the equation negative 31 is equal to 7 times q plus r. However, r is equal to negative 3 does not satisfy the inequality 0 is less than or equal to r is less than 7. According to the theorem statement, the remainder is assumed to be non-negative. So we cannot use q is equal to negative 4 and r is equal to negative 3 for our theorem result. For a third example, let's take n is equal to 54 and d is equal to 9. According to the theorem, there exist unique integers q and r such that 54 is equal to 9q plus r and 0 is less than or equal to r is less than 9. The unique integers q and r satisfying these conditions are q is equal to 6 and r is equal to 0. We have 54 is equal to 9 times 6 plus 0, and 0 is less than or equal to 0 is strictly less than 9. So what this means is that when 54 is divided by 9, we have a quotient of 6 and a remainder of 0. Now recall that an integer n is even provided that there exists an integer k such that n is equal to 2k, and n is odd provided that there exists an integer k such that n is equal to 2k plus 1. This means that an integer n is not even provided that there does not exist an integer k such that n is equal to 2k, or for all integers k, n is not equal to 2k. Now this is not the same as saying that n is odd. Using just the definitions, if an integer is not even, we cannot conclude that it is odd. The negation of the definition for n being even just does not match up with the definition for an integer n being odd. This result actually follows from the division algorithm, and we want to look at this now. Suppose we apply the division algorithm with a divisor d is equal to 2. The theorem tells us that for any integer n, there exist unique integers q and r such that n is equal to 2q plus r and 0 is less than or equal to d is less than 2. Now since d is an integer and d is greater than or equal to 0 and less than 2, then d must be either 0 or 1, which implies that either n is equal to 2q plus 0, or just 2q, or n is equal to 2q plus 1. In the first case, n is even, since it is 2 times an integer. In the second case, n is odd, since it's 2 times an integer plus 1. So the theorem then tells us that every integer n is either even or odd. Since the theorem also tells us that the q and r are unique, then an integer cannot be both even and odd. So thus each integer is either even or odd, but not both. It then follows that an integer that is not odd must be even, and an integer that is not even must be odd. We now want to show how we can use the division algorithm to introduce cases into a proof. For example, let's let n be an arbitrary integer and let d is equal to 4. What can we conclude about n using the division algorithm? The division algorithm tells us that there exist unique integers q and r such that n is equal to 4q plus r and 0 is less than or equal to r is less than 4. Since 0 is less than or equal to r is less than 4, and r is an integer, then r must be either 0, 1, 2, or 3. So the conclusion can be restated to say that there exists a unique integer q such that n is equal to 4q, or n is equal to 4q plus 1, or n is equal to 4q plus 2, or n is equal to 4q plus 3. And we'll use this result in the next example. So now we want to prove for all integers n, if n is odd, then n squared is equal to 8k plus 1 for some integer k. This has symbolic form for all n and z. N is odd implies there exists a k in z such that n squared is equal to 8k plus 1. We'll start our proof by supposing n is an arbitrary integer. Suppose the hypothesis that n is odd. We then need to show the conclusion there exists the k in z such that n squared is equal to 8k plus 1. That is, we need to show there exists an integer k such that n squared is equal to 8k plus 1. We want to introduce cases using the result from the preceding example. According to the example, applying the division algorithm with d is equal to 4, we can conclude that there exists an integer q such that n is 4q, or n is 4q plus 1, or n is 4q plus 2, or n is 4q plus 3. This gives us 4 cases. However, since n is odd, then only the second and fourth possibilities can occur. So we can conclude that there exists an integer q such that n is 4q plus 1 or n is 4q plus 3. This gives us just 2 cases we need to consider in our proof. For case 1, we're going to suppose there exists an integer q such that n is 4q plus 1. We need to show there exists an integer k such that n squared is 8k plus 1. Since we have an existential statement, we'll set up our 2 columns. We need to find a k and then verify that our k satisfies the 2 conditions. Since n is equal to 4q plus 1 in this case, then n squared is 4q plus 1 squared, which is 16q squared plus 8q plus 1. Factoring in 8 out of the first 2 terms, we obtain 8 times the quantity 2q squared plus q plus 1. And now this looks like our propositional function with 2q squared plus q taking the place of k, so we'll choose k to be 2q squared plus q. Moving over to the right column, since q is in z and z is closed under multiplication and addition, then k equal 2q squared plus q is in Z. So this satisfies our domain. And from the work on the left, n squared is equal to 8 times the quantity 2q squared plus q plus 1, which is 8k plus 1, so the propositional function holds. This proves the existential statement, so it proves case 1. For case 2, we suppose there exists an integer q such that n is equal to 4q plus 3. We need to show there exists a k in Z such that n squared is equal to 8k plus 1. So we'll set up our two columns for our existential proof. For this case, since n is equal to 4q plus 3, then n squared is 4q plus 3 quantity squared, which is 16q squared plus 24q plus 9. And we can break apart the 9, we can rewrite it as 8 plus 1. And then after doing that, we have a common factor of 8 in the first three terms. And so factoring the 8 out, we obtain 8 times the quantity 2q squared plus 3q plus 1 plus 1. And so now this looks like our propositional function with 2q squared plus 3q plus 1 taking the place of k. So we'll choose k to be this expression. Moving over to the right column, since q is in Z and Z is closed under multiplication and addition as usual, then our k is in Z. So our domain condition is satisfied. And then from the work on the left, n squared is equal to 8 times the quantity 2q squared plus 3q plus 1, which is 8k plus 1, so the propositional function holds. And so this proves the existential statement, so proves case 2. And since we've now proved both cases, then the conclusion holds.